So it's a pleasure to be here. So thanks everyone for coming. And we'll get started. My name is Trent McConaghy, and I'm with BigChainDB and Ocean. And I'm going to be talking about a few things, kind of like before as well, when Alex was talking about data and the Facebook Cambridge Analytica issues and all that. What's going on here? You know, what's at the heart of this? And I'm going to talk about that and some solutions we move towards having this. So to get started, in May of last year, of 2017, in May of 2017, there was an article on The Economist called The World's Most Valuable Resource, and it was about data. And it was about how data has become, well, so valuable that the most powerful, largest companies in the world have become that way because of data. And at the heart of it, we have things like Google, Facebook, Amazon, all these guys. And what they realized is that if they could gather lots and lots of data, they could refine it into having value. And they do that with AI models. And once they have AI models, they can use that to sell more ads, have a higher click-through rate, all of that. So they basically have this incentive to gather as much data as they can to make accurate AI models and then to turn that into money. And of course, they don't want their competition to have the ad selling abilities, so they hoard the data, they silo it, they keep it for themselves. And that's really the default incentive, is to hoard the data. Now, the incentives are a funny thing. Charlie Munger, who works with Warren Buffett in their investment, he said, show me the incentive and I will show you the outcome. So depending how you structure incentives, then you can get different outcomes. Now with blockchains, they're magic internet money, right? But what that means is you can get people to do stuff. So if there's something that you want someone to do, then you set things up such that you reward them with tokens, with magic internet money to do that. And that really is probably the biggest superpower of blockchains. It's not about the immutability, it's not about the assets, it's really about getting people to do stuff, right? And that's why, well, I have a superhero, because that's blockchains. So what's amazing then is when we have problems, and I talked about the problem of data here, right now the Schelling point, the default incentive is to silo the data, but what if we can change the incentives? So rather than for siloing data, what if we can incentivize to pool the data, right? That's what we're working on with Ocean Protocol, is incentivizing people out there, organizations, to pool their data to make it available to the planet. So with this, what most of this talk is about is actually not about the data, it's actually about design of the tokenized ecosystem that Ocean is. So we started out doing, like most people, lots of whiteboarding, right? Lots and lots of diagrams. Up on the right, that's an early algorithm that we wrote for computing impact of relative data sets. And there's different things there, different ideas, and we did whiteboard after whiteboard, and this was May, June, July of last year, iterating lots of different ideas, right? Saying, oh, what if we made Ocean look a bit like Steemit, right? What if we had reverse Dutch auctions, et cetera, et cetera? And then we started to try to refine more, like what are the overall goals of what we're trying to go for? What are the signals that might be there? Things like stake in the belief of a data set. What sort of tools can we have? And we explored and we explored, but it really felt like we were flailing. Where was the structure? And so we did this for 2, 3, 4 months, and we were trying to solve this problem, but it didn't feel like there was a way to really think about this, to know when we were done, right? And so we started to ask the question, can we structure this better? And around the same time, we started to realize something, and that was tokenized ecosystems are a lot like evolutionary algorithms. And I spent almost 20 years doing artificial intelligence, including a lot of evolutionary algorithms. And these are algorithms that are basically survival of the fittest, right? So you can have electrical circuits that you evolve against each other, you randomly sample them and so on, and then you breed them, you have parents, they make babies and so on, and over time you get better and better circuits, or better and better car designs, or whatever, right? So this is evolutionary algorithms. They're a very specific type of optimizer. And it turns out that if you think about this, and by the way, you don't have to think about just evolutionary algorithms, you can think evolution itself too, right? Survival of the fittest with species and all of this, right? But Tokenized ecosystems and evolutionary algorithms are really similar. They're similar in terms of goals, measurement and test, and so on. So for example, in an evolutionary algorithm, you have an objective function, something you're trying to maximize or minimize. For example, if you're training a neural network with an evolutionary algorithm, you might want to minimize the training error, right? Well, in a tokenized ecosystem, like say Bitcoin, Bitcoin is trying to maximize security, which is maximize hash rate, which is maximize use of electricity, assuming ASICs, right? So they each have a goal, and then you have a way of measuring how is that done. So in the case of evolutionary algorithms, you have a fitness function, right? Simulating a circuit, or measuring error. In blockchain land, we have proofs, proof of work, very specific types of work. You know, Bitcoin is solving a nonce, and there's other proofs as well. And you can keep going and keep going. There's different agents running around in evolutionary algorithms. But actually in blockchain land too, these agents are actually people who are doing mining. And they do whatever they want. They run around and you don't really care. All you care about is, at the end of the day, you reward them if they do things that add value to the system. And if they don't add value, then you just don't reward them. Or if you want, you can even punish them. You know, in evolutionary algorithms, you literally kill them off. In the world of blockchains, we don't kill anyone, hopefully, but we can slash their stake. We can they might have to stake, and if they act badly, then we can take that away. So overall, what I realized was I had been flailing, we had been flailing, and looking for structure. And we realized that evolutionary algorithms and blockchains are very, very, very similar. And you know what that means? It means that we can approach token design as optimization design, specifically as design of evolutionary algorithms. This is really great news because there was 40 years worth of history of designing evolutionary algorithms, especially since the early 90s. So this is a big field. There's thousands and thousands of people who have been designing this for years and years, and they've gotten incredibly good at it. So what is optimization design? What does it look like, right? And I'm going to teach you guys a bit about what this looks like and follow that with how we can apply this very practice to token design. In optimization design, there are 3 steps. First of all, you have to formulate the problem. What are the objectives, the things you're trying to maximize, minimize? What are the constraints, the things that have to be met? What is the design space? You know, where can the individuals run around? Then you try an existing solver. So use an off-the-shelf evolutionary algorithm, you know, some variant of genetic programming or NSGA2 or whatever. And if you need, you know, you try different problem formulations, you know, you switch around your objectives and constraints, or you try different solvers, right? And finally, you design a new solver, only if you need. So to formulate an optimization problem, this is a standard formulation here. You've got 1 or more objectives, that's the FI in the center. You've got 1 or more inequality constraints, and you've got 1 or more, or 0 or more equality constraints. And then you've got some sort of design space, right? This is just a standard thing. So for circuits, the objective function might be minimize power consumption, right? Once you have that, you try an existing solver. So this is running, for example, an evolutionary algorithm. The x-axis is the generations, which is the time intervals, and the y-axis is the cost, opposite of fitness, if you will. And you can see that it's converging in some runs, other runs not so well. But overall, this is actually, you know, it looks like it's behaving okay, right? But then if it's not behaving okay, and you've run out of the different solvers, you can't reformulate your problem, then you actually have to design a new solver. And this is an example of a solver that I designed, a variant of an evolutionary algorithm, published in about 2007 in some IEEE transaction somewhere. In this case, for circuit design, right? So sometimes you have problems where you really have to design that new thing, right? And it's using different building blocks below, you know, selecting parents in a special way, space filling individuals, and so on. And if it works well, then you can get nice results. So in that particular algorithm, what I ended up with, it would give me things like this. So it's giving me circuits, and in this case, it's actually literally a trade-off between gain bandwidth and power. So each dot in there is a different design. So this is an example of a successful outcome in design of an evolutionary algorithm or an algorithm following these steps. Now, we can now apply this idea from optimization design to token design. And the steps are the same, which is pretty cool, right? So first of all, formulate the problem, then try an existing pattern rather than algorithm, and finally design a new pattern. So formulating the problem, it's literally asking, what do I want this network to do? What am I trying to maximize or minimize, right? What do I want people to do? And then trying existing patterns. And there are emerging patterns. Some people are calling these crypto-economic primitives, right? And then finally, if you need, design a new pattern. So I'm going to walk through this in more detail and provide examples of it. So formulating the problem, where do these objectives and constraints come from? Well, in token land, in blockchain land, we have to first ask, who are my potential stakeholders, right? Who are the people that might be involved in the ecosystem? What do each of them want? What might each of them give, right? And then what are possible attack vectors? And each of those you can treat as constraints that you might want to try to solve for. And then basically, so once you ask those questions, you can actually translate those into objectives and constraints. So then you might say, okay, well, I've got these goals, these objectives and constraints. Now, what are existing patterns? How might I use these off the shelf? So, and there's actually a variety of different patterns that you can group. So there's a bunch of patterns related to curation. There's ones related to proofs of human work or compute work. There's identity patterns, reputation patterns, governance patterns, third-party arbitration, and more, right? And so a whole bunch of patterns. And to give you a feel for curation itself, there's a whole variety here. Many of you might have heard of something called token-curated registries. This is at the heart of an ad chain, for example. It's essentially a list that you maintain, a whitelist or a blacklist or whatever. And it's actually becoming so popular that at recent Ethereum hackathons, 1/3 of the projects used TCRs out of the box. So they're really easy to apply and use, and it's basically a way for the community to subjectively agree, is this person a good actor or not, right? But it doesn't stop at token-curated registries. Those are basically binary membership in some sort of set, right? But you can also have discrete values. Rather than a 0 or 1 binary, you can have 0, 1, 2, 3, 4, 5. This is a stake machine going from one level to the next to the next. We can have continuous valued membership, where people are putting their money where their mouth is towards higher and higher and higher value, and that's curation markets. We can go hierarchical with this, and we can even tie work to this. So there's a variety of patterns just for curation. And this is only emerging now, right? TCRs and curation markets are less than a year old. Or for proofs of work, right? So normally when we hear proof of work, we think Bitcoin, right? And Bitcoin is solving a cryptographic puzzle that some might argue that's not even useful, but it's actually maximizing Bitcoin's security, right? But we have lots of work out there. There's human work, like Steemit does or Augur does with prediction markets, but there's also computational work. And this can break down into two main patterns. There's data, and there's computation. So for data, we can do something like proof of space-time. Have you stored that file for the last 1 year on yourself? And that's actually what Filecoin has at its very, very heart. But there's other ones. There's proof of replication. There's proof of data availability. The TrueBit guys just published on that, and so on. Same thing for computation. There's a variety there. There's zero-knowledge proofs, things like ZK snarks and starks. There's interactive proofs, things like homomorphic encryption. Homomorphic encryption on its own is super cool. You can actually literally do compute on something that's encrypted. That actually does a very nice trade-off between privacy and compute then. So the summary here is that there's a whole variety of proofs. So when you say proof of work, it's not just solving some cryptographic puzzle. It could be one of many things. So overall, those are 3 steps, right? You come up with the objectives and constraints. You try with existing patterns. And then, if needed, you design new patterns. So I'm going to give 2 case studies. The first is analysis of Bitcoin. The second will be showing how I applied this new flow to Ocean. So Bitcoin, basically, if you look at it, and Satoshi led us all, and he just keeps teaching us. What Bitcoin is really trying to do is maximize the security of its network, right? And it defines security as hash rate. And hash rate comes down to compute power, assuming ASICs, right? And what this means is it's super expensive to roll back changes to the transaction log, right? So that's what Bitcoin is trying to do. We can write this mathematically, where on the left, the expected value, the expected number of block rewards coming is proportional to the hash power of an actor. So the expected rewards for actor I is proportional to how much hash power he's contributing times the tokens dispensed in that interval. In Bitcoin, it's 12.5 Bitcoins every 10 minutes, right? So basically, if you're actor I, if you're contributing 1% of hash power to the network, you can expect any given block interval to get 12.5 Bitcoin times 1%, right? So 0.125 Bitcoin. Of course, it's very lumpy, right? You either get it or you don't, right? So it's actually high variance. But interestingly, that's where mining pools come in, right? One level up. You have mining pools where if you contribute 1% to the network, then your mining pool, whenever it wins, you'll get your 1%. So mining pools can be viewed as variance reduction mechanisms. How well did this work? Going back to incentives, right? Well, How well did Bitcoin's objective function work in maximizing its security? Well, people are maximizing security. The hash rate is growing exponentially. It also means it's maximizing electricity, right? And Bitcoin is on track to use more power than all of USA by mid-2019. It's already using more power than most small countries, right? But this is kind of incredible, right? So if you want to see the power of incentives, magic internet money to get people to do stuff, there is no better example than Bitcoin itself. Let's go to Ocean. So the design of Ocean. So with Ocean, we really went and we approached it in this way. So first of all, we said, who are the stakeholders, right, towards formulating the problem? What do they want? And we listed the stakeholders. There's the data providers, there's the data referrers, there's the verifiers, there's consumers, and so on. And for each of them, they have value that they can provide and what they might get in return, right? So if I'm a data provider, well, I'm providing data. That's the value I provide. What might I get in return? Well, tokens, right, for giving it. That's a might. Of course, we have to decide later on. Then, once we have that, we have to translate into objectives and constraints. So the objective that we came up with Ocean, the objective function is maximize the supply of relevant data. Now, a big question here is, what is relevant? Do you want to let the algorithm decide? It's really, really hard. And there's been tons of research over the years to figure out what relevant data is, right? But let's defer that to the crowd. So let's say, instead of us deciding, let's let the crowd decide via curation, some form of curation. So then, it comes down to, we give token rewards if supplying data and curating it, right? But there's actually a whole bunch of constraints here too, right? So we came up with a checklist of things. For priced data, because we want Ocean to not only support marketplaces of data, but also to support a data commons, right? So for priced data, is there an incentive for supplying more? Is there an incentive for referring data? Is there good spam prevention, right? We don't want someone to upload some junk data set and get tokens for that, right? And same thing for free data, right? For data that isn't being charged for, is there incentive for supplying that? And so on and so forth, right? Are people incentivized to run keepers? Is it simple? So this was the checklist. And we also had about 3 pages worth of possible attack vectors. So, bullet point, bullet point, bullet point, a whole variety of interesting and different attacks. So once we had those objectives and constraints, so that main objective, maximize the supply of relevant data, plus constraints, that checklist, plus all the attack vectors, then we said, okay, what are some possible patterns that might solve for this, right? So we started off with the simplest thing that might possibly work, which is saying a registry of actors, right? A TCR or whatever. What might that look like, right? And also one just for data. Or what about a registry just for one for actors and one for data? And maybe starting to have curation. So how did those look, right? Well, against this checklist, the one that was just the registry of just data, of just actors, it passed only 2 of the 7 main checkpoints, right? And then it did so-so on a couple more, and it failed on the rest, right? So not very good. But the cool thing is, we know exactly what we're aiming for now, right? We have our objectives and our constraints, and then we can start to apply different patterns, right? On the second pattern, where it is the registry of data, well, it did well on some things and failed on others, right? And the other designs too, there's some passes, some fails, right? But none of them hit the target we wanted, right? So then we started coming up with new patterns, right? And basically, what if we have a data registry and then a curation market on the free data, right? Or what about an actor registry and a curation market on the free and price data, but also attaching work to that? And we tried those out. And you can see number 5, it actually passed a lot more, but it was only so-so on 2 things. But by the time we got to number 6, that pattern, it actually hit the whole checklist, right? And that is actually the core of the design we ended up with for Ocean. So we had a structured approach to hit that. So overall then, what does it look like in terms of objective function? Remember, we're trying to maximize the supply of relevant data. And what we're doing is rewarding the curating of data and making it available. And the thing is, if we just have a curation market where people are betting on the data and there sort of can be speculation on the data, that doesn't mean that the data is getting served up, right? So we said, you know what? You're only going to get block rewards if you curate on the data and make it available when asked. So it's binding together the betting that it's going to be popular and then the fact that it's actually popular. And that's what these 2 things are here. So there's predicted popularity, which is how much stake the user has in that data set's curation market, and the actual popularity, which is the proof that you made it available when asked, right? So the expected reward is proportional to the user stake, and did you serve it, times the tokens during that interval, right? In this case, of course, Ocean tokens. So we can see now we have a way of framing this that, that ties towards our objectives and constraints. But then we realized we actually had a few constraints out there related to privacy. And we kept finding ourselves leaning more and more towards needing to have on-premise compute or tying to decentralized compute networks like Golem or otherwise, right? So, so privacy was a constraint that we weren't quite satisfied with. And also, there's a lot of cases where data itself is super heavy, right? Petabytes worth. Are you going to try to serve that up every single time? Probably not, right? And also, there have been a lot of decentralized AI compute emerging, the generalized ones like Golem, or also the specific ones for AI, things like SingularityNet, right? So we wanted to tie that in, and we realized there's a way to do it. What it is instead of the predicted popularity of simply data, we can do it of a service, which can be data availability proofs or computation proofs, right? It can be multi-party compute. It can be whatever is coming from the network, hooked in through TrueBit or whatever. So that's basically what Ocean is about now. It's maximizing the supply of relevant services. So to start wrapping this up, what we started realizing was there's a new discipline that's forming. There's been a whole bunch of people writing about cryptoeconomic primitives and trying to come up with structured ways to design. And if you look around in all the scientific fields that are out there, there's game theory, which is sort of basically a scientific field for analysis of behavior. And then mechanism design is really for synthesis. But mechanism design and game theory are part of the overall broader set of economics. Economics is a science, right? Economics is not engineering where you're trying to deploy things, right? And we realized that once you take mechanism design and add in practical constraints, you actually end up with optimization design. But once again, it's not structured enough. And I'm trained as an engineer, and I realized, you know, as an engineer, we have great responsibility towards ethical behavior and so on. I'm a Canadian engineer, so we all get iron rings to remind us to be responsible for our designs. And so I realized is you start with optimization design, which has roots in mechanism design, but you bring in engineering, theory, practice, and tools, and responsibility. And that's basically what we've started calling token engineering for analysis and synthesis, right? So it's bringing engineering rigor and framing towards this. And rather than being, you know, stuck as a science, which, you know, science is, the objective function of science is to learn new things, to add knowledge to humanity. The objective function of engineering is to build things that work, right? So we're starting to call this token engineering. And that's what the title of this slide is, right? Of this talk is towards a practice of token engineering. What I described here is just like the first 0.1%, right? And as I've been starting to talk about this and write about this, a lot of people have come to me saying, I'd like to get involved, I'd like to get involved. And please, if any of you is interested, please come to me afterwards or DM me, TrentMC0. And really, what I described to you here is the story, the journey that we had with Ocean of trying to do a design, trying to do token engineering without a structure, realizing that there is a structured way to do this. It pulls in all this work on cryptoeconomic primitives, the patterns, and the overall flow is formulate the problem, the objectives and constraints. If try existing patterns, iterate, you know, and if needed, only if needed, try a new design, right? If you can get away with a curation market and that's it, awesome, do it, right? And this has helped a lot for Ocean so far. I'm not going to claim that it's the be-all, end-all because Ocean hasn't shipped, and you know, even after Ocean ships, we'll see. But it certainly helped us, and that's why we're sharing it now to see if it can maybe help some others too. Thank you very much.